Now that we have looked at the calculus of variations and some of its implications, we can draw our attention to Lagrange's equations of motion. For this, we will start with D'Alembert's principle. D'Alembert's principle is the most general way and in some sense the most useful principle that can be used to obtain Lagrange's equations of motion. I will start by making some assumptions, then I will state D'Alembert's principle, and finally, using some important results, I will give Lagrange's equations. The assumptions we will make are very straightforward. The first assumption is that we shall consider a system with one or more particles. Of course, the general case can be applied to a single particle. The second assumption we will make is that the external forces are conservative. This assumption will be somewhat relaxed until we get to the point where we can state Lagrange's equations, but to obtain Lagrange's equations in terms of Hamilton's principle, we shall assume this. And finally, we will assume that the internal forces obey Newton's third law of action and reaction. And by internal forces, I am referring to the forces between particles, not by some external applied field. Furthermore, we will consider forces that depend on the distance between particles. This leads to Newton's third law, as you saw in the fifth problem of the eighth homework assignment. If you do not remember what it is, please do look at it. I will use the following definitions for constraints. These have already been defined before, but it is important to know what they are. The first type of constraints are the so-called holonomic constraints. Holonomic constraints in our context are the constraints that can be written as a function of the positions and time. No velocities, no accelerations, just positions and time. And this constraint you must be able to write as an equality. If you can write it as an equality, you can write it such that this function is equal to 0. An example of a holonomic constraint is that of a rigid body consisting of two particles, where the distance squared between the particles is a constant. The proper constraint will be written like this. The other type of constraints are the non-holonomic constraints. As the name suggests, the non-holonomic constraints cannot be written in terms of equalities or in terms of the positions of the particles of the system. That is, there are constraints that involve velocities and are not integrable. Or the constraints are given in terms of inequalities. The simplest example of a non-holonomic constraint is that of particles moving inside a container of fixed volume. In one dimension, for example, this would be written as the inequality 0 is less than x, that is less than the length of the container, where x is the position of the particle, and 0 and L are the positions of the walls of the container. In our case, we will focus on the holonomic constraints. Important, from this point onwards, I will refer to holonomic constraints as constraints. If I want to refer to other type of constraints, I will call them by their proper name. Remember, we are working in 3 dimensions, so the position of each particle can be described by 3 independent parameters. A system of n particles needs 3 n parameters for a complete description. Now, we usually use Cartesian coordinates to describe the positions since they are easy to use, but there is nothing that limits our choice of coordinates, other than that they need to provide a complete and consistent description of the system. In general, the Cartesian coordinate for the ith particle represented by Ri, for an n particle system can be parametrized by 3n parameters. For our purpose, we will use a Q to label the parameters, that they themselves are functions of time. So the Q parameters are functional. It is important to highlight that the constraints can be used to eliminate parameters from the resultant equation or equations. One of the important things to notice is that these parameters do not necessarily form a vector coordinate system. That is, the parameters may be, for example, angles, lengths, or some other quantity that properly describes the position of the particles in the system. Now, the role of the constraint equations is to relate the parameters and eliminate some of them. In general, if these constraints are consistent, that is, independent, for each constraint we can eliminate one parameter. Thus, the number of parameters for an n-particle system will be 3n minus k, where k is the number of constraints. For convenience, instead of labeling the parameters with a double subindex, we can use a more convenient notation by using one single index that runs from 1 to 3n. If you only see one index, it just means that the index runs through a certain number of parameters, with constraints already accounted for. Now, just be aware that this is just notation. In reality, this is not extremely important since each parameter is independent and you can do this for whatever number of parameters that you have. So, for the moment, just assume that the ith position is a function of the n parameters and time, where n is an integer number and represents the number of independent parameters that you have. It is important to understand that Newton's second law is very hard to write down, especially for systems where there are multiple constraints and it is unclear how to set up the forces, both magnitude and direction. This was solved by implementing Lagrange's formulation of mechanics. Lagrange's equations can be obtained in several ways, but one of the most powerful ways is to use D'Alembert's principle. D'Alembert noticed that each particle has a particular force equation such that the net force acting produces a change in momentum with respect to time. That is what we saw with Newton's second law. Thus, for the ith particle, we can write the resulting differential equation. We can now subtract the change in momentum with respect to time on both sides such that we have an equation that is equal to 0. Written this way, it means that I can always find the force that counteracts the net force applied to a particle. This is somewhat similar to what we did when we were proving the work energy theorem. We now take the work done by this force and add over all the particles. This might sound weird since if we know that if the work done is 0, what else can we do? The answer is that we want to find the relations between the generalized coordinates, and this procedure will extract that information. And this will be done in the next video.